Okay, this is an example of how to find the capacitance of a cylindrical capacitor. So what I've given you here is an inner cylindrical conductor in red of radius r is equal to A, and an outer cylindrical conductor of radius r is equal to B, and there's a space between them, which is, in this case, will be filled with air. Theoretically could be filled with a dielectric, but in this case we'll just leave it as air. And the idea here is that I've only given you a segment, right? That's why I've put the black arrows in to show you that this actually continues. Because in practical matters, in the real world, when you buy a cylindrical capacitor, you're probably buying a cable. A coaxial cable is an example of a cylindrical capacitor. You probably use these to connect your cable box to your television, or your DVD player to your television, or whatnot. If you're not using HDMI cables, you're probably using coax. This is a real-world example of a cylindrical capacitor, and you know, if you think about it, you can go to a spool of coax cable and cut off as much as you want. And so, to talk about the capacitance in general of a coax cable is impossible. So, what we typically do with that is we talk about the capacitance per unit length. We take the we find a representative length of the cable, measure the capacitance, divide through by that length, and what we get is the capacitance per unit length. And that way, whatever size cable you cut off, it's very easy to find the capacitance. You just multiply the capacitance per unit length by the length of the cable, and you get out the capacitance of your particular cable, right? It's the same idea as a mass density. A mass per unit volume tells you, in general, how dense something is, and then if you have a particular example of that substance and you know the volume, you can find out the mass just by multiplying it. So the capacitance per unit length is a property of the material. The capacitance is a property of a specific example of that material. So what we're going to find here is the capacitance per unit length. And so I've given you a representative length, length L. The inner conductor has a charge of positive Q. The outer conductor has a charge of minus Q, as it has to. Their magnitudes have to be equal, as they do for capacitors. And I've given you the general formula for potential difference in terms of the electric field and a path length. So first thing to do is figure out what the electric field is. We actually know this from previous results when we did Gauss's law for a line of charge, which is just a cylindrical conductor if you really think about it. Even if it's a line, if you zoom in close enough, it's probably going to be a cylinder. So we know what that is. What we found that to be is 2K, that's a terrible looking K, K lambda over R, where lambda is the linear charge density. In this case, I'll write it up here, lambda has to be Q over L, right? The linear charge density. I believe when we did this when we did this problem, what we found was that the electric field was 1 over 2 pi epsilon naught times lambda over R, but 1 over 2 pi epsilon naught is just 2 times 1 over 4 pi epsilon naught, which is K. So I've written that as 2K. Now I've got to find the vector form of this because my equation involves a vector, and we also know that result from previous, we know that that answer from previous results. The electric field is everywhere radial. There are no components along the length of this conductor because of symmetrical charge cancellation. We're going to assume that we're far enough away from the ends to avoid any edge effects, any funky electric field. So it's going to be everywhere radial, right? If I were to draw that, at least the two-dimensional version, it would look like this. And of course, keep in mind there are field lines coming out of the computer screen at you. There are field lines going into the computer screen away from you on the other side of this thing. But there are no horizontal or lengthwise components, and it's everywhere radial. So to express that, I just slap an R hat onto my electric field and a vector sign over E, and I've got it. So now I need to come up with an appropriate path length ds. Hopefully by this point in the semester we're starting to see the process. I need something that's going to cancel with the R hat of the E field, and so I'm going to pick my path along the radial direction. And we know what that is. In cylindrical coordinates, that's just dr. To make it a vector, I have to give you the direction, R hat. And that's what makes this integral almost trivial. I've got an R hat in the E field, an R hat in the ds. They're going to dot into each other and produce 1, which I can just ignore because 1 times anything is just that thing. And if I plug all that in to my equation over here, I get that delta V is equal to minus the integral from A to B of 2k lambda over r dr. I've already taken care of the dot product. I'm just left with a scalar. And I get, this is minus A to B, minus 2k lambda integral from A to B of dr over r. And we know what that integral is. It's just the natural logarithm of r. So this whole thing is going to be equal to minus 2k lambda log r evaluated from A to B. Now at this point I can just apply some of my rules of logarithms. Log b minus log a, which is what I'm going to get out of this, is just log b over a. So I can write minus 2k lambda log b over a. Let me go to a new page, and now I'm going to express lambda, remember what lambda was, q over L, in terms of q over L. You don't have to do it at this point, but you will have to do it eventually, because what we're interested in is characterizing this thing in terms of its parameters, of which one is L. So let's go to this page and do that. So delta V is equal to minus 2k q over L, that's my lambda, log b over a. Alright, that's a terrible looking A, try to do that better. Alright, so now let's form the capacitance. Capacitance is the charge over the potential difference. Now remember, this is a little bit tricky to remember. Capacitance is a positively defined quantity, so all I'm interested in here is the magnitude of the change in potential. Just how big that delta V is without regard to the direction in which I'm traveling, because if I go back to my original, if I flipped my charges, in other words, if I had a minus Q on the red conductor and a positive Q on the yellow conductor, well, if you think about it, my capacitance wouldn't change. My capacitance is in some ways a measure of the, well, it's not in some ways, it is exactly a measure of the charge I can put on this thing per unit of potential difference. So the capacitance wouldn't change. So I want to define this in a positive way so that I don't have to worry about the direction that I'm moving. The direction of delta V sounds strange because delta V is a scalar, but the direction in which I'm moving from one capacitor to the other. So I'm just going to nix the negative sign here, and what I get out of this is that that's Q over 2K Q over L log B over A. Alright, so my Q's are going to go away as I expect them to, because my capacitance is only calculated using physical parameters. My L is going to flip up to the numerator, and what I get is that this is L over 2K log B. Man, it's hard to write with your fingers. Log B over A. Now, if I'm interested in the capacitance per unit length, you guys can probably see what's going to happen here. I just divide through by L, and I get my capacitance per unit length is equal to 1 over 2K log B over A. Alright, so something interesting here is that in this form of the capacitance per unit length, for this particular arrangement for the charged cylinders, you have to be very careful where you set your 0 point for potential, because you run into problems. If you set it at point A, well, then you run into a problem there because you're dividing by 0. If you set it at point B, you're also running into a problem there because what is the natural log of 0? That's problematic. So you have to take an arbitrary point. When you're dealing with these cylindrical conductors, you have to take an arbitrary point to set your potential to 0. We typically set it at infinity. That's a little more difficult here, but that's okay. That doesn't really have anything to do with this problem. I just think it's interesting.